Fine. So you can get going.
Yeah. Okay. Thank you. Thank you
So
very
the title
much.
is on planar solutions in high spin theory, as you can all see. Please.
Yeah, I'm very thankful for invitation to this conference, and also it's a pleasure to see people that I didn't see quite for a while. Like Augustus in particular, I didn't see for ages, and Per Sandel, it took a really while that I didn't see. I'm very happy to see. So this work that we're still doing with Anatoly Karibut is devoted to planar solution in high spin theory. It is based on some already published paper and the other that we're in a position of writing up. But basically, the ideas that work is based on are not new, and they go back to my investigation with Mish Vasilyev and Alex Matveyev long ago. So the motivation of planar solution in high spin theory is kind of twofold for us. But there are physical aspects like what kind of generalization of general relativity black holes could be in high spin theory. That might be some naive way to construct just by controlling only the symmetries, but maybe it works after all. And this related thing to it is that it might as well be some higher spin bulk site for safety thermal states, like they do in normal gravity theories, ordinary gravity theories. But apart from that, there is some, and also something that I cannot comment at the moment. It can provide some high spin locality tests at high orders. But then there are some mathematical aspects of business. Like we know in general relativity, black holes are algebraically special. So if there is something similar happens in higher spin, and also very much related to that, we know that GR black holes possess this linearization property, which the double copy stands upon. And so the natural question is this also true for high spin solutions? So this is basically my motivation, and I start with known thing with the black holes in ADS4. Here you see the metric, which depends on some discrete parameter k here, which can be either 0, +1, or -1. There's the mass parameter and the ADS radius L. And these metrics described for k equals +1 the Schwarzschild solution in ADS4. Whereas for k equals 0, it has the planar horizon. The planar, this two-dimensional planar here. And for k equals -1, it is what is known as hyperbolic black hole. And you see, for that matter, for instance, for a planar solution to exist, you really need to have a non-zero cosmological constant. So the horizon radius is proportional to it. So this kind of coordinates at m equals to 0 provides you with the Poincare patch of ADS4, and for m away from 0 gives you deformation. Okay, so we're going to be interested in this case k equals 0 and its higher spin generalization from that perspective. The symmetries of that solution are very explicit. It does not depend on t, so it's stationary, in fact static, and also it has this symmetries of two-dimensional plane. And as well as the other cases in gravity, that solution is known to have what is called a hidden symmetries. There are many ways to present this hidden symmetries. One way of seeing them is that if you look at the curvature tensor, then it requires only linear in M contribution, whereas all possible high order name corrections vanishes. And there's a way to approach this linearization through this Kerr-Shield answers, which Dario in his talk have shown already. So the black hole matrix can be decomposed into a part which depends on the background G naught and a fluctuational part which has a kind of a degenerate form built of light-like vector L, which is actually is geodesic. And those properties are not enough for Einstein equations to hold. So actually you need more, you need the linearized equations, Einstein linearized equations to be fulfilled. And then it guarantees that the solution is linearly exact. So at this stage, it is not even clear why this Kerr-Shield vector should even exist, that obeying all these properties. But in fact, it obeys even more than this. It's particularly this function u here, it generates you free scalar fields. So 1 over u satisfy a conformal Klein-Gordon equations in 4 dimensions. Then if you take L over U phi, then it's going to satisfy Maxwell equation. And this is what is known as a double copy property, which to my surprise was observed only in 2014. Even though I suspect there must be something in its twisty literature many years before that. So this is the paper of White, Connell, and Montero, where they checked that black holes do possess double copy properties in Minkowski asymptotic Minkowski spacetime. So how we generalized the results in a bit earlier for ADS black holes, and we showed that if you take these Kerr-Shield vectors actually satisfy multi-copy relations, so that field here satisfies Fronsdal, free Fronsdal equation for motion in ADS spacetime for more or less all black holes in 4 dimensions. So it looks quite peculiar, but the reason for that linearization is this hidden symmetry, which is actually very simple. It turns out that all these black holes has what is known as Killing-Yana tensor structure. So in the language of Cartan equations, hidden symmetries are not much different from ordinary symmetries, and let me demonstrate how it works in practice. So consider some space with curvature R, where W is Lorentz connection, E is the frame field with no torsion. Then the origin of symmetries can be traced back as follows. For example, let's take some vector t here and act with a covariant differential on it. And what you generally have is something which is symmetric and antisymmetric. And if you further impose, for instance, the symmetric part vanish, then the resulting vector would be a Killing vector. You might well ask for just graceful part to be present in this symmetric part. And on that occasion, you get the conformal Killing vector. So you can take a somewhat more complicated structure, for instance, the antisymmetric tensor TAB. And when you act with the covariant differential on it, you have general decomposition here that consists of rank 3 antisymmetric tensor, some hook-like tensor H, and vector N. And then you may play this game by requiring something to vanish. For example, if you set the hook 0, then if the spacetime is consistent with this condition, then TAB is called the Killing-Yana tensor. You should also require N to be 0. Or just H equals 0, this is called conformal Killing-Yana. And even more stringent constraint that you can set H and R equal to 0, then the resulting TAB is called a closed conformal Killing-Yano tensor. And this is actually what all four-dimensional black holes possess, this closed conformal Killing-Yano. And actually some of the d-dimensional generalization over Kerr type, let's say, they also have like a closed conformal Killing-Yano. So you may wonder, others like similar examples where the Killing-Yano may appear, and such space is just ADS space. So consider the Cartan equations for ADS space, where the curvature is given by this cosmological term. And then this formal equation has a nice feature that it has local gauge symmetry. That is, if you vary W and E in the following form with kappa and V sum 0 forms arbitrary parameters, then you will see that the Cartan equations remain invariant. And then if you set those variation to 0, you will find global symmetry. And that global symmetry, those conditioning exactly gives you the condition for a key where you can recognize that the parameter V here is a Killing vector, because the right-hand side is the antisymmetric tensor. There is no symmetric part. Well, this kappa AB antisymmetric contains no hook and no antisymmetric rank 3 tensor. And that is why this is a closed conformal Killing-Yano. So you see in ADS space-time, those fields go hand in hand, and they can be unified to form the global symmetry parameter of D-1, 2 algebra. Okay, so long as we are in 4 dimension, following isomorphism will be very useful. It allows us to rewrite that global symmetry parameter in the form of this 4x4 matrix metric, where kappa and V fills here spinorial representation of this vector objects, being 2-dimensional matrices. Kappa is symmetric in alpha and beta. And the equations for global symmetry parameter acquire this form, this simple form. Again, that was shown many years ago, that if you take this global symmetry parameter, then you can construct some tensors that has a form of wild tensor of gravity in the following way, and they will be exactly correspond to 4-dimensional black holes of any kind. So it could be, it may contain a knot parameter if M is complex, and so you see that this metric enjoys double copy relation in the sense that it is a product of 2 Maxwell tensors that are originated from this kappa and R variable. More generally, this is what is called the D. Petrov type representation for wild tensor. So you see that we have generated black holes from ADS global symmetry parameter in an ADS covariant way, and this implies that the amount of non-trivial solution of that kind are in one-to-one correspondence with the number of orbits of global symmetry parameter. Particularly, you can impose some extra condition, ADS invariant condition. For example, of that kind, that k squared is equal to up to a coefficient to 1 or 0 unit matrix or 0, And that condition is invariant with respect to a joint action of ADS group. And so this case, assuming that you also started with some time-like killing vector in that parameter, corresponds to 3 cases. So the k equals to +1 is the Schwarzschild solution. That was considered in Yashin-Evan's talk. K equals 0 to planar black hole, k equals to -1 to hyperbolic black hole. And this k exactly corresponds to that k parameter in the metric had been given in the first transparency. So we're interested in planar conditions. So from now on, we impose it. That said that k squared is equal to 0. And we're going to explore that case in more detail. And one of the remarkable facts of that extra condition is that once you impose it, you would observe that there is an extra flat connection, one form, that you can construct out of ADS Lorentz connection, its Vierbein field, and the vector k, which is constructed from the fields that enter global symmetry parameter. So the k here is kind of important, it squares to 1. And then if you associate to that connection a covariant differential in the following form, then it turns out to be nilpotent. To check that, you need 3 conditions. The first one is the ADS conditions, that is the Cartan equations for omega and E. Then you need the conditions for global symmetry parameter, and you need this planar condition k squared equals to 0. Only on that occasion, you will have this nilpotent. So it's a kind of accidental connection, but it will play a very useful role in our machinery constructing solutions. With respect to this connection, it turns out that the fields kappa and V properly normalized with this determinant of kappa turns out to be covariantly constant. That will be also very useful in what follows. Then from these 3 conditions, it follows that the vector k here itself is covariantly constant. And as such, it can be used as sort of a metric that converts in dotted indices into undotted. And we adopt this notation. So whenever we say dotted spinor index, we can convert it into undotted using this k. And that statement will be invariant with respect to Nabla operator as well. Using that property, the planar condition is equivalent to, can be rewritten as a statement that these 3 fields that enter global symmetry parameter, kappa V and kappa bar, they all actually the same up to index conversion. Okay, so then another property of that connection that you can find some analog of Vierbein postulate, that if you introduce the one form constructed out of ADS Vierbein properly normalized, then it turns out to be covariantly constant with respect to Nabla. Then it will be convenient to decompose it into symmetric part, epsilon alpha beta, and antisymmetric E, so that both components are covariantly constant. And in these terms, this auxiliary flat connection gets written as follows. So these are the prerequisites, some requisites that I will need in constructing solutions in higher spin for higher spin equations. So let me start with the higher spin story. So I'm going to use the unfolded Vyacheslav approach that starts with equation on vacuum, higher spin vacuum. So W naught is a connection that satisfies the equation of flatness in higher spin algebra, which is spanned by this Moyal product acting on auxiliary variables wise. The only polynomial solution to that equation is at the ADS spacetime. Any other solution will necessarily contain higher spins. And for the linear equations, they sit in two different sectors. The one is the twisted adjoint sector that contains field strength equation and the matter fields. The equation for it looks as follows. It contains this vacuum connection, contains the zero form C, that is some master function in Y space. There's some sign flip pi here, that the reason that model is twisted adjoint rather than adjoint. And the meaning of those components, for those who are not familiar, are as follows. So the one which is not depend on Y's at all, it's just a scalar field. So those that have the same number of indices, dotted and undotted, describe derivatives of scalar field. And then there goes the field strength parts of Maxwell tensor, like this Weil tensor, and the higher spin extension. And any mixed components describes derivatives of the spin S field strength. The other sector that contains gauge fields, which is called the adjoint sector, looks as differential, covariant differential, ADS covariant differential action on gauge fields gives you their strength. This is the meaning of that equation. So you see the zero here just means that only Weil tensors contribute on the right-hand side, higher spin Weil tensors, rather than their descendants. There is a phase parameter eta and eta bar here, which is irrelevant at free level, but plays a role at non-linear level. It distinguishes the phase space of higher spin theories. In what follows, we succeeded in what is called as higher spin A model, which corresponds to eta equals 1. Now, these are the physical components that corresponds to Franzel fields in master fields W. So those are the components that carry the same amount of indices dotted and undotted. The rest are auxiliary. And now we're going to solution. So the simplest sector is the twisted adjoint sector. It can be solved by using the sort of unfolded Penrose transform that was also in Yash Neyman's talk. It guarantees, so the idea is to take arbitrary function f that depends on the global symmetry parameter K capital here. And once it is K satisfy adjoint condition, then any function of f with some extra twist provided by this star product with delta function gives actually the solution for twisted adjoint model. I skip the details, but the result is as follows. So this is the direct calculation. And what we see here selected by red is that this exponential contains exactly this metric K alpha dot that was used in the construction of auxiliary flat connection. So recalling the convention of contracting dotted and undotted indices, the solution can be rewritten as follows. And the content of that solution is the following. So the spin S Weil tensor is given by this generalized D Petrov type. It is very conveniently parameterized by this function f. So any monomial term in M of the degree S corresponds to some spin S field activated at free level. For spin equals 2, it gives you the planar black hole solution. And for arbitrary S, it gives you natural generalization. This unfolded Penrose transform guarantees that the symmetry, the global symmetry, are all right. It corresponds to planar and static symmetries of the solution. And now there's a very important property that all the fields for any spins contain one of the same derivative tail hidden in this exponential, which is somewhat special in star product algebra. It turns out to be a Fock projector. It's going to play a huge role at nonlinear level, particularly whenever it finds its twisted version. It is going to provide a naked infinity, and this will be somewhat also a test whether we have such infinities in higher spin equation or not. So in their local form, no such infinities occur. The boundary behavior of the solution corresponds to S plus 1 dependence on R for spin S. And you see that here we're missing the alternative boundary condition for S equals for scalar field. It was not captured by this Penrose transform. So to be generic, we can add it. So there is a planar solution with delta equals to 2 boundary behavior, and we can add it if necessary for nonlinear analysis. But it was not captured by the Penrose transform. So this sector was pretty easy. The first sector is the joint one. You may remember from Mitya Ponomaryov's talk, for example, that the solution for field strength are usually easy, even in the case of plane wave solution, but the gauge sector can be quite complicated. So the idea of solving the joint sector is to rewrite covariant derivative using this extra accidental Nabla derivative. And then in these terms, any nz's of W field of gauge fields that depends only on fields that enter global symmetry parameter, those kappa V and kappa var. Upon some normalization, they will be just constant with respect to Nabla. And that means that the partial derivative equations, space-time partial derivative equations, will reduce to ordinary one. And for eta for the phase parameter equals to 1, we were able to solve that equation to find the solution in very, very simple form. That was one of the inspiring things to go on to nonlinear level, because the solution is very simple. So with this solution of adjoint and twisted adjoint sector, we go to nonlinear level, to quadratic. And the first equation that one encounters with is the corrections to the twisted adjoint sector that you can extract, was extracted by Vasiliev from Vasiliev's system. Here the subscript 2 means the second order corrections. 1 means these are the free fields, so we are in perturbations. And generally, Vasiliev's system is in 4-dimensionally supersymmetric. That's why there can be, it contains 2 copies of each spin, and that's why there might be different kind of embeddings of free solutions. So we consider 2 pictures. One is the bosonic embedding. They labeled those two different copies with this extra operatic line operatic, which is called K. This is technical detail. But then there is other natural embedding, which we called chiral embedding, have no better name, where in one sector goes fields with mostly positive chiralities, and to the other mostly negative. And so we plug into the equation using the following substitution. We subtract this focal projector by introducing this new field T. And it turns out that the structure of interaction here is very specific, that eventually the focal projector factors out from both sides of the equations, and the resulting equation is polynomial in y and y bar for a given spins.
So how much more do you need?
I need 5 minutes. Is it okay? Or how much still?
Okay.
I can be even quicker, 4 minutes, I guess. So then, so the right-hand side is what comes from the interaction terms, and to solve that equation, we first know that if we assume that it depends on our set of fields, then this operator nabula will not contribute that part in one form sectors, meaning that that piece should be equal to that separately, and that implies a stringent consistent constraint for right-hand side, which does not follow from the consistency of higher spin equations. So it should be checked separately. And it turned out that for chiral embedding, static condition does not hold, meaning that we cannot prolong our free solution to nonlinear level, keeping still planar and static altogether. But for bosonic embeddings, it works. It's a bit of non-trivial calculation, but it works. And it gives you the static solution and we solve that equation. The corrections turns out to be, I skip the details of the coefficients that have to be double checked yet, but the solution turns out to be still of Petrov D type. And one can, for example, ask whether in pure gravity case, whether this sector remains somehow protected, whether the gravity fields remain within the sector 2, activating no other fields. This turned out to be not the case, as gravity induces actually also spin 4. And this is in agreement with Shankarin proposal that there should be no purely black hole states in higher spin theory that contain only spin 2 field. But what surprisingly, the spin 0 turned out to be somehow isolated, meaning that any spins in interaction at this level do not produce correction to spin 0. Whether the linear approximation exact, the answer is no for finite number of spins. For infinite, we're not able to check that. Maybe there are solutions, but for finite number, this is not the case. And this is unless you consider only scalar field. And this opens some possibility of unexpected new solution, which contains only scalar field propagating on ADS background. So it solves the first non-trivial part, nonlinear part of the equation, but whether it solves all vertices, analyze all vertices is yet to be checked, and this is part of something that can be done. So I'm ready to conclude. So what has been done, we sort of set the stage for perturbative approach for searching planar solution of higher spin equations. And this approach includes the generating technique of global symmetry parameter from ADS spacetime and the use of accidental flat connection that was very useful. So we found solution at free level for higher spin A model in a very simple form that allows to go on to nonlinear level, and calculated the quadratic corrections that turned out to be algebraically special. They turned out to be still of D type. That's very interesting fact that perhaps it means that within this Dipetrov type ansatz, you can go on further. And some unexpected thing is that the scalar sector has decoupled from this analysis and received no correction disorder, suggesting a possible exact solution that contains no spinning state. So thank you very much for attention. Sorry for some delay.
Thank you. And if anybody wants to ask Slava a question, this is the time to start. Then after a couple of questions, we'll go to the discussion session. I think we will start from Juan and go in order. This would be my proposal, so that we keep everything. So anyone who wants to ask Slava a question? If there is no one, maybe I will ask you one question, Slava. Oh, no, Juan is asking. You want to ask a question, Juan, or you're ready to receive questions? Do you hear me?
Yeah, I'm ready to receive questions. Yeah.
Receive questions. Let me ask one question to Slava, and then we pass to you. Slava, my question is the following. A few years ago, when you did this first work with Misha on the black hole story, which is one that I followed at the time. Now, I wanted to connect this old work with what you're doing now. Can you say in a few words what is it?
So what was known at that time, so we constructed some solution of spherical symmetry in higher spin theory that looks so far a bit formal because we didn't address the problem of the locality issue, and that solution, I guess, should be reconsidered. But apart from that, it is some solution and some ingredients for analysis in different cases, like planar case was already established there. I mean, this generating technique in terms of global symmetry parameter.
So the key point is that you're addressing locality issues now somehow.
Yes. Now we're addressing this issue, exactly.
Okay, very good. So I guess we can, if there are no other questions to Slava for the moment, we can go back, resume Juan.